pleasure to be with you here today, this morning, after the last time I was here 4 years ago, I think. So it's a bit of an update of some of the things that we are doing in the university. So I'll talk about vehicle track interaction in switches and crossing and why it matters. Let's see. So first of all, I'd like to talk about the wheel-rail interface in a bit more detail and look back to some of the principles around this and what's specific about switches and crossings and why we do seem to have a lot of issues and challenges with this. Then I'll talk about some of the simulation tools that we've been working with and developing over the years to help us understand this from a more fundamental or fundamental physics point of view and how this can help. Then I will talk a little bit about the role of the universities, maybe in supporting the industry in doing R&D and innovation, and some example of what we've done over the years. I'll talk about the need for field measurements and validation. And then finally, I'll expand on to what I think are the next things that will come in the future to try and integrate some of these technology for design purposes, remote condition monitoring, and maintenance prediction. So first of all, some of the issues that I've been observing since I worked in this area. So this is a site where we see a crossing panel that the crossing is right in the middle here, and you can see a lot of vertical movement from all the bearers. So the vehicle passing over the crossing creates dynamic loading that will eventually sort of degrades the condition, especially the support of the track. And it's not really concentrated purely on the wheel rail at the wheel load transfer, but you can see in this case there's a lot of voided bearers and a lot of movement that spread along this specific casting. If you look more closely, this is the same video but zoomed up, so you can appreciate a bit more the movement. So if you simulate the ideal condition of the design, you should have about 1 millimeter of deflection, by design, but in reality you get a lot more, and then eventually that can lead to a number of problems. Another example in a switch panel, again, a lot of vertical movement around the POE, so you can see there are locations where the system is dynamically responding a lot more than you would want from a design point of view. And then if you go further along, it deflects a bit less, and then more again around the POE. So you have a whole panel that does sort of motion as the train passes. So again, probably not ideal. So some of the issues that then arise from these, the state condition of the system is, major issue is obviously the crack and failure from the foot of the casting. On the long bearers that we talked about this morning and different design, this typical network rail design also suffers some damage because they get stressed, and you've got vertical loading on both sides of the track. With crack bolts and so on. We may eventually have cracked bearers. Some other aspect on the right-hand side here is very uneven surface of the wheel and the rail. So this might be caused by repair, or it might be caused with some combined vibration of vehicle and track. You'll be familiar with probably a lot of these type of defects, so that's purely related to the wheel-rail interface itself and the high stresses we get in the rail, and the high crippages as well. So that's the differential speed between the wheel and the rail in the areas of the switches. So I won't go through all of these, but I'll go back to some of the theory around a wheel set rolling on rails to try and explain the fact that we get high energy going into the contact. So that might be obvious for most of you, but maybe not everybody. So we have in railways a rigid axle and conical wheels. And if we do this, that means if we displace the axle one way, we'll have a higher rolling radius on one side and a smaller rolling radius on the other side. That means that one wheel is going for one rotation, one wheel is going to travel more than the other one. And that will eventually push the axle back towards the central direction. It will eventually overshoot because of its inertia. And then you'll have the opposite with a higher radius on the other side. So we've got a self-steering mechanism, essentially, that helps us align the wheel set along the track, and that's very handy because in curves that means the vehicle steers on its own at a fixed equilibrium position without the need for actually the driver steering the train. So that's what that's how it's designed. It works perfectly fine. But what happens when we come into a switch and a crossing? We basically compromised, the good work we've done in shaping those profiles to achieve self-steering. In a switch, we would tend to then machine the stock rail, introduce the switch rail. The stock rail will move sideways before we get into the switch toe, one of the rails will start diverging. That means, again, there is a differential of rolling radius between one side and the other, and you automatically generate some steering onto the axle. And then it actually steers in the opposite direction to the one you would like the axle to steer, because you've got the smaller radius on the left-hand side. So that creates a moment onto the axle that yaws, and then it will tend to either be eventually going into contact with the switch, so you can have fairly harsh normal contact, high stresses again on the switch, but you also have a lot of differential speed on the top surface of the stock rail. So that's what generates your squats and RCF over time after many wheel passages. So we want to try and minimize this. Pardon. So there are a lot of design options to do that, and kinematic gauge widening is something that has been trialed and done, and so that helps a lot. But we're talking about very small things there that are there to help adjust and steer things better. Now, when we come to a crossing, the major thing is your wheel rail impact load. So I'll just try to illustrate again what's happening. Again, that's probably fairly obvious to most people, but maybe not everybody. So what happens is that the wheel travels along the crossing, and then the wing rail starts moving away from the wheel. So we get a contact that moves towards the field side of the wheel set. So again, that means smaller radius. So the wheel will automatically change direction. It will introduce a moment. And then eventually, second contact point will come on the nose, and then the wheel will climb back up the crossing nose. You might think that's probably very small, but if you simulate this for different wheels, these are the vertical trajectories of different wheels over a crossing. So we can see the characteristic dip angle that's being talked about this morning. And that can change based on the wheel and the position of the wheel. These two angles makes up the dip angle value. And that's where your dynamic amplification load occurs. So you get a very high force on the crossing nose, which is weaker than a normal rail, so you've got high stresses and deformation again. One other thing I'd like to point out is when you come to the leg ends, you change the shape of the rail very quickly, and you also get vertical input to the rail, to the wheel, and you get also some dynamic forces happening. And in some cases, we've simulated things that are even higher than the load transfer area. And we know it's an issue. There are failures occurring as well at the leg ends, and there are voided bearers there. Another way of illustrating, we get a vertical motion, downwards and upward motion of the wheel. So we're trying to ask this wheel to accelerate back up, and that's what creates the typical P1 force, very local damage, high frequency, and then the P2 is the wheel set rebounding on the track. That creates more energy going into the track, and leading to some of the casting failures and voided sleepers. Okay, so that was just a review again of some of the basic physics around switches and crossings. So in terms of the simulation tools that we've been working with and developing over the years, I'll do a review of that again. So first of all, we started looking at understanding that wheel motion for a crossing. So if you take a wheel shape and you take a crossing shape, you can roll it and then find out the trajectory of that wheel if you assume rigid contact and rolling, pure rolling. And that gives you some information about the vertical motion of this wheel for certain design. And then you can feed that back through a simple mathematical model that replicates your wheel and sprung mass and your track mass and the spring stiffnesses. And then you get an output force. So that's a good way of quantifying this different design. If you want to go more sophisticated, you would use vehicle dynamics simulation. So that's an example of a vehicle running through a switch, and you can see the arrows there represent the suspension, reaction, forces. And then you have fairly detailed wheel-rail contact. So you can understand the normal stresses and the shear stresses that will lead you to the damage that you want to quantify. So in terms of complexities, the top one is very fast, runs in seconds. The multi-body dynamics might be running in minutes, so it's still valuable because you can really run a lot of scenarios. If you're interested in these solutions, we recently published a benchmark, an international benchmark comparing all this software that was very well followed by industry and academia. So that's a resource you can look at. If you want to understand better what's going on along the track, then you have to do slightly more sophisticated models. So if you want to understand the vibration of a rail or a casting, then you need to model it as a beam, and then you potentially with discrete support, and you can introduce variable support stiffness. So we've developed some in-house software to do this. You can also integrate fairly detailed flexible track model into the vehicle dynamics I was showing before, where you can have detailed vehicle dynamics, detailed wheel rail contact, but also the distribution of the track and how the load will distribute along the track. So we've done some projects developing a complete turnout, looking at long bearers, looking at introducing gaps below the bearers to capture what's going on. And we can also couple this with some settlement calculation. So you can do the short-term transient dynamics and then the long-term voiding underneath the bearers. But again, you start adding complexity. Once you get into this, you might be talking about a few hours of simulation. If you do settlement, that might be coming to a few days of simulation. Eventually, the most complicated or advanced simulation tool is finite element based. This is a crossing panel with a wheel rolling over the crossing area. So that's again more detail. You would look at the very short P1, P2 impact over a short period of time. But you can get stresses in the components of interest that are subject to failures and look at specific design refinements. You can introduce plastic material into the crossing nose to understand plastic deformation and residual stresses in the crossing nose. With these tools, the problem is that becomes quite heavy to use and possibly days of simulation, so it's difficult to really embrace all the other conditions coming around this that might influence certain crossing or certain design. To support our simulation, we've developed, as part of a European project that Phil mentioned before, we developed a tool to recreate the input geometry for any switch and crossing we wanted to work with, because that's a fairly long process. The input data is difficult to generate, so knowing the cross-sections of the rail, we can extrude them. Knowing the machining tools and shapes and path, we can extrude and recreate all the input data we want to those simulations. So then you come into an area where you have, say, the multi-body system simulation tool available, and you can put different vehicles running over certain crossings. You can consider facing and trailing move through and diverging, and you can vary the speed of those vehicles. You can look at the suspension effect and unsprung mass. And then you can feed in different design shapes. So Phil mentioned some design work we've done for NR56 crossings. We literally looked at hundreds of shapes of crossings. So you go into thousands of simulation, and then you look at the impact force, and then you decide which shape is best based on the actual physical impact force you'll get from the wheel rail interface. So that's very valuable insight into what's going on. Okay, so over the years, we've worked a lot on research projects, and this is a list of projects we've participated in the last over 10 years. Most of these were funded by the European Union. So we're coming to the end of Shift to Rail, Horizon Europe is there. There's a bit of uncertainty. We're waiting on the Prime Minister possibly to sign something so we can carry on with these type of collaboration work, but that's been very beneficial to work at a European level. In the UK, we've been benefiting from EPSRC grants, so it's the Engineering and Physical Council Research Council. So we've had some grants, typical 3 or 5 years that allows us to do the research, and usually we do this in collaboration with Network Rail or other industry partners to try and get some inputs and discussions going on. We have a framework existing, which is Ukraine in the UK. So that links together the university doing research in railways. So Birmingham is one of them. Southampton, I'll mention later in some slide, and we are as well, and the other universities as well. But that creates a point of contact as well to work with industry, and that's Ukraine is funded 2/3 by industry as well and 1/3 by the government. I can't go into details of all these projects. There are too many, but you can be in touch later on if anything is relevant to you. I'll mention some of the works we've done directly with industry. So we also do direct consultancy and problem solving. We've participated in evaluating the wheel rail interface and interaction on on the NR60 Mark II development. We looked at the Newark Diamond Crossing together with Progress Rail as well. And so again, looking at variations in the shape of the crossing to try and optimize the final solution. We looked at high-speed turnout geometry, linking between HS2 and the standard railway, just deciding on clothoidal versus other type of design used in Europe. All this doing some simulation work. Also did a lot of work on revision to TRK012 standard some years ago. That was presented 4 years ago at the PWI. So in all this, simulation is great. It's very good, and in universities we obviously like to work with these and develop these tools, and usually they take time. But the question is always about how validated or how true are they. So I'd like to discuss a little bit about field validation and laboratory test and the need for this. So I've got a list of questions on the left-hand side I'll go through later on. But we did some work trying to validate our tool, especially in the PSRC project Track to the Future, together with the University of Southampton, where we monitored the wooden gate sites on East Coast Main Line. So that was the first turnout, I think, installed with USB at the time, with 2 different types of USB, fairly soft ones. And then we went several times to the site to monitor, measure its reaction with traffic running. And then eventually we got some traces of deflection along the entire route of the turnouts, and we try and match this with our simulation software. And what we get, I think I've lost the laser, but if you look at so we had accelerometers, geophones, in various places monitoring the bearers. The deflection on the graph is the deflection at different bearers along the turnout. So you've got the switcher toe on the left-hand side, the crossing on the right-hand side, and in the middle you actually have a joint or a rail weld. So we calibrated the model, so we changed the stiffness to try and get the same deflection to understand how variable the stiffness was. So we could replicate the variability of the stiffness and the support condition underneath the bearer from the model. But it wasn't enough to achieve the actual displacement we were seeing. So the yellow shaded areas are the voids we needed to introduce in order to capture the right deflection. So that allowed us to understand actually how much void is being created. And obviously, most of the crossing panel is voided. The rail well, the tracks, actually the major deflection at that site. So that's an area where as well there's localized damage, intervention that will have to be done. And the leg end area as well is one other area where, again, you get a lot of voiding. But also transversely across the sleepers, we actually had to create a lot of voiding there to get the right results. So we know that transversely things are not smooth, not homogeneous, and the collars of the long bearers were also broken, evidently, where we had those voids. So as well as they work initially, they're not designed really to withstand the type of load and stresses they get on track. So this is more and more, it's always difficult to get access to site, and you probably don't want some sort of people coming from universities walking down your track. I know your priority is to get trains running, so access is always a tricky question. So we don't get the chance as much to do those type of measurements, but I think it's important, so we need to keep trying. There's a question about number of sensors we need. This site was instrumented all the way through. As you do things more, you maybe learn what sensors to use and where to put them, so you can maybe get faster, minimize the disruption. More and more we start using remote sensors rather than wired ones, so that allows us to then put stuff in the track and leave it there, and then you can come back to your seat in your office and check what's going on. We'll start moving from track to vehicle-based measurements more and more, inevitably, but I think we do need to understand specific site and monitor them carefully to understand what's going on when you run a vehicle over. Measuring what's happening short-term over a day with specific vehicles, specific wheels is important, but the long-term settlement and evolution of settlement is another thing that is difficult to measure and capture. There's some unknown as we go down into the track. We can understand and visually see the superstructure, and so we can try and model that as accurately as possible, but once you get below the ballast, there's a lot of unknown, so it's very difficult to capture and model and understand exactly what's going on and where any fault how it's triggered. It's difficult to measure directly the wheel-rail interface, so in terms of quantifying, understanding the forces directly, usually we just look at acceleration or stresses in the casting, try and infer the forces going on. In terms of laboratory testing, these can be a good way of getting some results, some validification of the tools faster, more safely. So easy access, fast to set up, we control the conditions. Some of the drawback, however, is how realistic they are. And some examples, so this is the University of Southampton doing tests on a previous project where we collaborated on a single sleeper, so it's great. You can test effect of an under sleeper pad, different loads, but it's only one sleeper isolated from the rest of the system, so you then have to try and extrapolate that back to a full track condition. We recently carried out some tests on our full test rig called Harold, so that's as a buggy, and we took a piece of track of 13 sleepers, and we changed the support stiffness, and we introduced some voids, and we measured vibration with hammer testing, and then cyclic loading through the bogie up to 25 tons. So that allow us to capture some data that will be useful to understand and what the model, how to calibrate the model, what the model tells you. Can you interrogate the model to tell you about voids? How big are they? Where are they? Those type of things. Twin disc. That's something we do to measure wear and rolling contact fatigue, but it's scaled, so there's always a bit of an issue of scaling it back up to full scale. And these have been done mostly to look at plane line conditions, but when you come to switches and crossing, the high stresses you have, the high crippages, so far that has not been really tested with those type of tools, so that remains to be done, I think. Okay, so that leads me to the last sort of discussion points of this presentation. In terms of what all we've done is trying to help achieve better design from the start, concentrating on the wheel-rail interface. So that's something I'll still send that message and talk about it a lot. But we are looking at a system, so we need to understand the vehicles going, the effect of certain vehicle on the system, the effect of speed, the effect of suspension. The wheel-rail interface is at the heart of some of the issues we have, so we need to understand that and try and capture it more realistically. And then that needs to influence what we do about the component superstructure and the design of the support underneath the SNC. All the work we've done shows that if you know your wheels, you can actually design much better crossing, and we're currently doing this. So if you have a dedicated high-speed network, you can actually design a crossing that's going to be nearly perfect for that specific wheel. And so if you can understand your local conditions, you can probably better design. Obviously, it's difficult to do, but maybe you can better maintain your asset. So we're working on some tools to understand the wheel shape, how that should drive the shape of a crossing if you repair it. Adding resilience in the system is very important. So we can't avoid the impact load in a crossing specifically. So you really need to have to mitigate for that and spread it. So the superstructure needs to be designed in a way that it adds some resilience. It allows the spreading of the load, not just to one bearers, but across a number of bearers. The leg ends are still an issue, and that's not something that has been looked at in too much detail, but there are failures there that we need to look at. You need to be able to continuously monitor and measure the system. And I think we're slowly moving towards vehicle-based monitoring over time because that's less intrusive, but we still need to understand the system from specific site monitoring. As we are developing black box AI, machine learning, data intelligence around all these sensors and data we're capturing, if we make it open, people will be able to develop faster some intelligence around it. Physics-based model should be there to really anchor it into physics and engineering, so we already understand what those algorithms are telling us. Right, I'll zip over this and I'll go straight. I'll just acknowledge some of my colleagues. It's not my work. Plenty of people I've worked. I've been the pleasure to work with a lot of people in the last 10 years. Some are still with us, some have gone, but I'd like to thank them. My new PhD student is here in the room. He's on the right-hand side there. This picture, you should see him today, and he's sponsored by Network Rail and just starting looking at SNC condition monitoring. List of publication, I won't go through this, but you'll have the slides, so if you want to see anything that we've done, they are there for reference. And I thank you.